Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello everybody, welcome back to another episode of the A-Level Cookbook. Today we're going to be doing the AQA A-Level Chemistry paper from June 2019. So it's paper 2. So this question's about amines. Give an equation for the preparation of 1,6-diaminohexane from the reaction of dibromohexane from an excess of ammonia. So immediately what you should always do is start by writing what you know straight away. So we know it's going to be 1,6-diaminohexane, right? So it's going to be a CH2, and there's 6 lots of them with BRs on either end, like this. And we know that we're adding some amount of ammonia, right? Then we need to think about the products that we're going to make. So if we're adding ammonia, it's going to swap with the BRs. So it's a substitution. And because ammonia has lone pairs and is going for a carbon that's electron deficient, that means it's nucleophilic substitution. So then what we're going to end up on the other side is we're definitely going to have an H2N instead of these BRs now. CH2, 6 lots of them, and then an NH2 on this side. But then remember that in the mechanism, what happens is you actually end up having too many bonds on this nitrogen when it first joins. It ends up being H3N, which is too many, and it breaks them off and then takes those BRs as well. So you actually end up with 2 NH4 BRs as well. So that's how you do that one. Complete the mechanism for the reaction of ammonia with 6-bromohexylamine to form 1,6-diaminohexane suggests the structure of a cyclic secondary amine that could be formed as a byproduct in this reaction. What a tongue twister, my god. So what we've got is we've got our NH3 chill in here, and you can see that this bond is broken here. So when you're drawing mechanisms, don't just memorize the arrows, think about what the arrows are doing. Every arrow that you draw is an electron pair moving from one place to another. So this bond between this C and the Br, for example, the electrons are going to this Br. Something must have triggered that to begin with for it to boot off the Br like this. And it's that a lone pair from this nitrogen has formed a bond with this carbon here like that, right? So if that's happened, then as a result, the next step that you end up with is you end up with this same thing here, right, NH2, but there's actually there's an NH3 here, but there's a plus because it doesn't like having 3 things on it because that's lost that lone pair. So in order to, if I just rewrite this a bit better, sorry, we've got a plus, H, H, and H. The solution to this is to either boot this off, but that doesn't make sense because we've just stuck it here, or boot one of these H's off. Now, if we want to kick the H's off, we're not going to draw the electrons going this way because each of these bonds is a covalent bond, right? If we did that, we'd end up with 2 plus on this end, which we don't want. The whole point is trying to get rid of the plus. So what happens is this bond breaks and the electrons go from the bond to the N from the H. So what you end up with is you've got this H plus, but then that's still not happy. So what happens is you've got an NH3 that comes along and gives a lone pair of electrons to that to form NH4 plus and mopping it up like that. Now, it says we're making a cyclic secondary amine somehow. We need to think about what's happening. For as long as you have a Br in this thing and something that has a lone pair of electrons, it can swap. However, with this thing that's doing the swapping is something that has a lone pair. If you look here, there's a lone pair of this nitrogen here. So what this can actually do is it can swap with the Br there and link itself like that. So what happens is you end up with NH, and then the rest of it stuck together. So it's 1, 2, 3, 4, 5, 6 carbons. So what we end up getting is an NH with 6 carbons coming out. So 1, 2, 3, 4, 5, 6, like that. Sorry, no, wait. That's 6, sorry, is it? Let me just double check. 1, 2, 3, 4, 5, 6. Yeah, that's 6. Whoopsie doodle. There you go. So be careful you should be able to identify immediately what groups are in it and think, oh, this could do this. For as long as you've got lone pairs on something, it can do nucleophilic substitution. So 1,6-diaminohexane can be formed in a 2-stage synthesis starting from 1,4-dibromobutane, suggesting the reagent and condition for each stage in this alternative synthesis. So what we're starting with here is we're making 1,6-diaminohexane, and we're starting with bromobutane. So we've got a halo alkane, and we're going down. We're switching to diaminohexane. So we've now swapped the bromo for amino. So we need to think of another route to get to there. One other route you can take, rather than just obviously doing the obvious NH3, is you can swap it with something else with an N in it. We need to think of what we could put an N in. So one thing we can do in stage 1 is you can swap it with a CN- ion, like this. So then what we can use is we use our reagent. It's not going to be CN- ions. You need to say what the actual thing is that you're going to put in that provides CN-, right? So, and you also can't do this in acidic conditions either. So you use KCN or NaCN, right? And the reagent and condition, well, that's the reagent. The condition is that it is aqueous, and it's aqueous in like an alcohol like ethanol. You can't use an acid here because then it just doesn't work. So then it says stage 2 reagent condition. So now we have this thing, instead of bromos, it's now got this C triple bond N on it, right, like this. So we want to turn that down into an amine. We've got to reduce it. So what we do is we use H2 and then a nickel catalyst as well. There you go. So now it says, explain why 3-aminopentane is a stronger base than ammonia. So anything in the world that accepts an H+, as in joins with it, is a base. So let's just compare them side by side. So 3 amino pentanes, so 1, 2, 3, 4, 5, right? And then there's a 1, 2, 3 aminos here, right? And there's the lone pair, whatever. And then it's versus ammonia. Something about these two is making this a better base. It's better at accepting H+. So the only fundamental difference between these two is that this one has a whole group of CH3s on it and this has nothing. So something about these CH3s here makes this better at bonding with an H+. When it's bonding with an H+, it's giving those lone pair of electrons to the H+ like that through a dative covalent bond. So it must be that these electrons are more easily given to the H+, which is exactly what it is. So in 3-aminopentane, the lone pair of electrons on the nitrogen atom accept H+ better because they're more readily given away. So they're more available. We need to think about why. It's because those alkyl groups are essentially pushing the electrons in that direction. So pushing electrons that direction. Or you could say it's the positive inductive effect. There you go. Whereas if I had, for example, benzene stuck to it instead, right, with an NH2, it's actually less available because that benzene is dragging those electrons into its pi system like that. It's a lot better at doing that. So because they're less available, it's actually a worse base. So it says, justify the statement that there are no chiral centers in 3-aminopentane. It's because no carbon atom has 4 different groups. The only thing that makes a carbon atom chiral is whether it has 4 different groups. And if you do draw this, which I have up here, you can see that there's this NH and there's an H there, but these two are the same on either side. There you go. So student prepared cyclohexene by heating cyclohexanol with concentrated phosphoric acid. The cyclohexene produced was distilled off in the reaction mixture. Complete the diagram for the apparatus needed to distill this. So we need to add like a bung here to stop everything leaking out from the top because we don't really want to do that. We want it to go down this route, right? But then we also have to have a thermometer at the level at which the gas is there, right? At the level at the sidearm. So this bung is going to go there, and as well as that, the thermometer too will as well. And I'm going to draw this like that. There's your thermometer as well. And then it needs to be no gaps. As well as that, we need the condenser itself, the jacket. So we're going to draw the condenser like this. And then we're going to add the water coming out like this. And the water going in like this. So water in and water out. The reason we do it this way is so it doesn't accumulate and pull down here. It's always so that it's continually cold water passing through them. So the distillate was shaken with a saturated sodium chloride solution. A cyclohexene was separated from the aqueous solution using a separating funnel. State why cyclohexene can be separated with a separating funnel. The entire point of a separating funnel is that you have 2 layers of things that you want to separate. One is aqueous, one is the other, the organic, right? Now, sometimes it could be at the top, sometimes it could be at the bottom. It depends which one's more dense. But the point is you're separating them on the basis that they don't mix. For example, if you mix oil and water, they don't mix, right? So that's how you can separate them, by literally just letting that level set out and then just removing whatever bit you want. So the liquids don't mix, or you could say they are immiscible. There you go. Now it says the cyclohexene separated in this was obtained as a cloudy liquid. The student dried this cyclohexene by adding a few lumps of anhydrous calcium chloride and allowing it to stand. Give one observation to make sure that this cyclohexene was dry. Well, if you're drying it, what happens is that it is no longer cloudy. And it also tells you, kind of in the question, that it was cloudy to begin with. So if they're doing that, it's probably going to make it not cloudy. So in this preparation, the student added an excess of concentrated phosphoric acid to this many grams of cyclohexanol. The student obtained this much cyclohexene, and the density is that. Calculate the percentage yield of cyclohexene obtained and give your answer to appropriate number of significant figures. So any question where you're about to do anything to do with moles or anything, you must write an equation even if they don't give you one. Not like a fancy one, just literally the things that you care about and what ratios they work in. Otherwise, what are you doing? What's the point? You're just going to do random stuff and then fumble. So here we are starting with cyclohexanol. We're doing whatever to it, this and that, blah, 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 and we're making cyclohexene. Now we're only swapping one group and stuff, so it's going to be a 1-to-1 ratio, and then here as well, let's add in what we know. So in terms of cyclohexanol, we know we have 14.4 grams, we know its MR is 100, and on this side, what we know about this is that it's 4.15 centimeters cubed, and we know its MR is 82, and we know its density is going to be 0.810 grams per centimeter cubed, or grams Cm minus 3, right? Now they want us to work out the percentage yield. Percentage yield is going to be your actual over your theoretical times 100. So in order to do that, we need to find out theoretically how much we would get of this. We can use the ratios here because we know it's a 1-to-1 ratio now because it's only one thing that's been swapped to make this thing, right? So in that case, the moles of the cyclohexanol is going to be its mass, so 14.4 over its MR, which is 0.144 moles. Then, in theory, we should get this much cyclohexene in that, right? So our mass of cyclohexene, theoretically, would be its moles times the MR, which would be 0.144 times 82. And if we do that, we should get 11.808 grams, right? so we've got our theoretical, but we need our actual. So in terms of our actuals, we need to look at what they've given us. They've given us the density of it, and they've given you the volume. Now, if you ever get stuck, and it's sometimes people genuinely just do find it tricky to remember things like, density equals mass over volume, considering it's not like actively told. The units tell you what's up. It tells you this many grams for a centimeter cubed. So it means that 1 centimeter cubed gives you 0.810 grams. Grams per centimeter cubed. When you see per, it means like every one of those gives you this. So kilojoules per mole means however many kilojoules per 1 mole. For 1 mole, you get this, right? So if I have 1 centimeter cubed giving you this, then 2 centimeters cubed would be 2 times that, right? 2 centimeters cubed equals 2 times 0.810. So then if we have 4.15 centimeters cubed, then it's going to be 4.15 times 0.810 grams, right? So then, in that case, the amount that they've actually got in this equation is going to be 4.15 times 0.810, which is 3.36 grams. That's our actual yield. So then, the percentage yield is just going to be 3.36 divided by 11.808 times 100. And if we do that, we should get 28.45. We should try and follow the number of significant figures in the question, so 28.5%. Bingo! Now it says cyclohexene reacts with bromine. Complete the mechanism for this in the reaction. So again, don't just memorize like arrows and which way they go. Think about what's happening. Br2 is happy. It's not got any difference in electronegativity. There's no reason for it to just split like that. So something's happening to basically piss off this bond and make this go here. So what's happening is that this floating around nearby here puts a dipole onto this. Remember that covalent bonds are shared pair of electrons. Simply by just being near this thing, it's pushing those electrons to the side here like that. So you start to get dipole where that's delta positive, that's delta negative. What happens is this is now becoming an electrophile because it wants electron pairs. Electrophile attracted to electrons. Phile attraction 2. So what happens is we need to think of where we want to get electrons from. It's going to be this lovely fatty double ring here. So an arrow comes from here to here, showing the movement of electrons from the ring to this bromine. And the problem is this bromine's now got too much on it. It only likes bonding with one thing, but now it's got this and this. So the only way to fix this is it's like, I got to boot something off. So what it does is it boots off this here. The way I like to think of it almost is that now these electrons have come here. The electrons that were in this covalent bond have been shoved even further onto this to the point where they've practically been nabbed by this, right? That's how I kind of think of it to make sense of it. So then what happens is that breaks off, that bond's gone, and this is now stuck here. So what you end up with is now you've got this with a single bond, because that's gone, with a Br on it. And then the other carbon, remember, is now missing an electron. So you have a carbocation here, because it would have otherwise had a hydrogen here. But then this bromine has now got a Br minus, and it's got a lone pair. So what it does is it gives the lone pair to the carbocation like this. I could draw that a bit nicer, sorry, whoops. Like this, here. Can you see how it's actually donating its lone pair of electrons to this carbocation? It's technically acting as a nucleophile here. So that's how electrophilic addition works. That's the mechanism. You should always think about it in steps, and if you get stuck, you can kind of just look at what's happening here. You know roughly that you're going to make, dibromocyclohexane. So the outer layers of some golf balls are made from a polymer called polyisoprene. The isoprene monomer is a non-cyclic branched hydrocarbon, and it contains this much carbon by mass, and it says the empirical formula is the same as its molecular formula. Deduce the molecular formula. So it's told you it's a hydrocarbon, meaning you're only going to have C and H's in it. They've told you there's 88.2% carbon, so the other, however much, 11.8%, should add up to 100, right? So it's going to be that. So then what you do is you divide them by their MRs to work out their respective moles. So then you would end up with 7.35 here to 1, right? Now, the thing is here is that, sorry, not to 1, to 11.8, right? Now we need to divide by the smallest number, so you're going to get 1 to 1.61, and then we need to try and figure out timesing by a number to get it back up to, whatever. So if I times both sides for like 5, for example, 1.61 times 5, I end up getting on this side 8.05, and there you go. So it's probably going to be C5H8, right? It's just a general case of just timesing the numbers by whatever until it looks like it's very close. If I do 3, it's 4.83, 4 is 6.44. If I do 5, it's 8.05, which is really close to 8. So you can say it's that. Then we need to deduce what the structure is, right? So they've told you here, though, carefully, it's a branched hydrocarbon, and it's isoprene, and it's got this formula, C5H8. So if it's branched, what we're going to do is I'm going to draw 2 carbons, and then I'm going to stick a branch of it of some sort, and, add things up, right? So 5 carbons, 2 of them here, 1 there, and then let's go with 1 here, and then 1 here. So that's 1, 2, 3, 4, 5, right? We have 8 hydrogens to work with. We need to figure out how to divvy them up and do what we can with them. Sorry, 8 hydrogens. So what I'm going to do is I'm going to say that's a CH3. That's what? How many left? We've got 5 hydrogens left. So I can't put a CH3 here because then we've only got 1 for each of these, which ain't going to work. But we have double bonds in this because it's isoprene. So what I can do is I can put some double bonds in to use them up. So if I put a double bond here and here, for instance, then this is 1, 2, 3, 4. That's happy, right? This is going to be 1, 2, and then I could put 2 hydrogens here and then 2 hydrogens here. So that's happy. And we've got 1 hydrogen left, so I can put that there. So it's 1, 2, 3, 4. Then 1, 2, 3, 4. Sorry, that's that. And then there's 1, 2, 3, 4. 1, 2, 3, 4. So it's kind of just doing it like that. Now, the insides of some golf balls are made from a mixture of 3 other polymers. The repeating unit for one of these is shown. Draw the skeletal formula of the monomer that made this polymer and give the formula. So you're not drawing the repeating unit. They want you to know what this came from originally. So they want the skeletal formula. The original formula of this thing would have been that, and these gone here like this. So we need to draw it skeletally. So it's going to be a carbon with another double bond like this to the carbon, here, right? And then it's going to have another carbon next to it with nothing, right? Just a singular bond. And then another carbon with a double bond again to another like this. There you go. Now, the name for this is it's 1, 2, 3, 4, right? So it's a bute something, or butar, right? And we're going to know it's alkene, so it's going to end in ene, but there's 2 alkenes, so it's going to be diene. So then we need to put the positions of them. So it's between 1 and 2, so there's 1, and then 2 and 3. So it's going to be, 3 and 4, right? So that's going to be butyl 1, 3 diene. There you go. The second polymer in the mixture is a repeating unit with the structure shown. The third polymer in the mixture is a stereoisomer of this polymer. Draw the structure of the repeating unit of the third polymer and then explain why this stereoisomerism arises. So you should be able to recognize that there's 2 groups here and 2 groups here that are different, and there's a double bond in the middle. This is stereoisomerism, EZ isomerism specifically, or cis-trans isomerism, because you've got hydrogens on each. If you had 4 different groups, like on either of them, then it's EZ, but cis-trans is fine. But either way, regardless, here, it's going to be C+C with the groups on the opposite sides instead. So it's going to be CH2 with a long thing in here, and then an H2C like that with the long bit out there. So they're on opposite sides, right? So then the reason is that there is restricted rotation around C+C. You can't rotate these. If it was just a single bond, then these can just swap positions, like they can just flip like this freely. Whereas because there's the double bond here, it's fixed like this forever. So this one's always up here and that one's always down there, which can change the structure of things significantly. Golf balls recovered from lakes and ponds can be used again, even after being in water for several years. Explain why they do not biodegrade. So the only reason is that it must be that we can't hydrolyze them. Biodegradable means that we can hydrolyze them, put water in and break them, right? So in this case, it's because these C+C cannot be hydrolyzed. Polymers like polyesters and polyamides can be. Like peptide bonds, for example, you can hydrolyze those. That's because they're polyamides and they're made from condensation reactions, so you can use hydrolysis to break them apart. Substances P and Q react in a solution at constant temperature. The initial rate of reaction was studied for 3 experiments by measuring the change in concentration of P over the first 5 seconds of this reaction. The data is shown in Table 1. So it says complete Table 2 to show the initial rate of reaction in P for each experiment. So all you've got to do is, can you see that they're measuring their end of the reaction at 5 seconds, right? The rate of reaction is the change in your reactant or product or whatever you want to call it, some substance, over the change in time, right? So if we're looking at experiment 2, the time is 5 seconds that it's changing it. So the change in time is 5 seconds. The change in the reactant of product is going to be what? 2 times 10 to the minus 2 minus 1.84 times 10 to the minus 2. If we do that, we get 3.2 times 10 to the minus 4. So that's all it is. I think people get too rate equation pilled, and they're like, wait, I don't know the rate equation, bro. I don't know what K is. It's like, no, that's not the point. They're making you go back to basics, and that measuring any rate in the universe is just looking at something being produced or lost, or pH change is literally something changing over time. A rate is that, how something changes with time. In this case, they're looking at concentrations of P and Q. So we're looking at the rate of change of P and Q. In this case, they're looking at the rate of change of P, which is how much its concentration changes over time. So in this case, you would do the 0.5 minus this divided by the 5. If you do that, you should get 3.2 times 10 to the minus 4 as well. Would you look at that? Then it says determine the order of reaction with respect to P and the order of a reaction with respect to Q. So if we look at here then, with P, what have they done? In experiments 1, 2, and 3, so in experiments 1, it was just 1, then they changed it to 2, and then 0.5. So between 1 and 2, this is 1, it's been doubled, this case stayed the same, but the reaction between 1 and 2 went up by what? Times 2, right? Because these are the rates we just worked out. So remember, here we had 1, but now it's 2. This is the same, rates doubled. So that means that the order with respect to P is first order, because you've doubled the concentration of P, and the rate doubled. Now I need to look at Q. So between here and here, nothing's changed. Between here and here, what's happened? 1.2 to 2.5. This has been times 2. And then if we look at P, then it's gone what? So it has become halved, right? So then in experiment 1, the rate initial rate was 1.6 times 10 to the minus 4. Experiment 3 was 3.2 times 10 to the minus 4, right? If we look at what happened between these two, we see that's doubled, right? But we've done what we've done to P, we've halved P, so therefore the rate should times by a half. But can you see how it's actually doubled? So the rate times a half times some mysterious thing gives you times 2. as in a half times something gives you times 2. So that mysterious thing has to be times 4, right? So if we've doubled Q, and the rate has also gone up by a factor of 4, which has then been halved to give you that double, that means that doubling Q, rate's going up by 4. Therefore, it's second order with respect to Q. The way I like to think of it is rate proportional to, like, for example, A, right? If it's first order, then if I double A, I get 2A, so then I get 2 rate. Whereas if it's like A squared, if I'm doubling A within the bracket, I've got to square the double, so then that's going to be 4. If I have 3A and it's squared, right, then I'm going to have to do 3 squared times the rate. That's what's changing. And if I have, like, I don't know, if it was to the cubed, then if I had 7, then it would be 7A. I've times A by 7, but I've got to do 7 cubed to the rate. That's how you make sense of it like that. A reaction between substances R and S was second order with respect to R and second order with respect to S. At a given temperature, the initial rate of reaction was this, and when the initial concentration was this and this. Calculate the values of the rate constant for the reaction of this, and then give your units for K. So it's always just tricky to look at what's going on here without writing just the basic rate equation first, because there's so much wording here. Rate equals K times whatever, right? So it's told you here that it's second order with respect to R, and then second order with respect to S. So that's definitely our equation. They want the rate constant. So rearrange it first, then put the numbers in. Please don't put the numbers in and then just try and rearrange it and try and be Captain Underpants. Like, it just doesn't work. Because you'll write utter garbage. You won't get any method marks because the examiner will literally not be asked reading all of that garbage you've written on the page. Rearrange first, then put the numbers in, because then they can see you've tried at least attempting to rearrange it, you know? And you can still get some method marks there. So we're looking for K. K is going to equal the rate divided by this and divided by this. So it's going to be R squared times S squared, right? In that case, now we put the numbers in. So the rate that was here was what? 1.2 times 10 to the minus 3 divided by R, 1 times 10 to the minus 2, but squared, and then S, 2.45 times 10 to the minus 2, but squared. If you do that, you get 19991, right? We want the same number of significant figures, so that's roughly just 2 with all them zeros, which is just 2 times 10 to the 4. So then we need to work out the units. So in terms of the units, we're looking at rate, which is in mole dm minus 3, s minus 1. We're dividing it by, these are both measured in moles per decimeter cubed, but it's to the power of 4. So it's going to be mole dm minus 3 to the power of 4, right? Now you can think of this almost as mole to the power of 1 dm to the minus 3, s to the minus 1, all over mole 4 dm minus 12. Because if you've got brackets like this and you're raising something with indices to a power, you're multiplying them. Whereas if you're like adding indices, so if you're timesing indices, like 2 to the 4 times 2 to the 6, you add them. But if I do 2 to the 4 all squared, then I'm timesing these. Here, if we're subtracting these, we're subtracting the powers. So you've got 1 minus 4, which you end up getting as mole minus 3, right? And then it's going to be minus 3 minus 12, which is going to be dm 9, and then the s minus 1, there's nothing here to do anything with it, so it stays as s minus 1, and that's going to be 2 times 10 to the 4. Bingo. In this question, it says, regrettably, this question contained a typographical error, which affected some students' abilities to answer it. All students were awarded full marks for this question. Okay, so this question is about isomers. Give a reagent and observations for a test tube reaction to distinguish between 2-methyl-butan-1-ol and 2-methyl-butan-2-ol. So what you should do is always compare the two that you're working with first, right? So it's butan-1-ol, so there's an OH here, and there's a methyl here, right? Whereas the other one, it's 2-methyl-butan-2-ol. So it's this with a methyl and the OH here. You should be able to recognize immediately primary alcohol versus a tertiary alcohol because there's a methyl group here. You can't oxidize a tertiary alcohol, which means if you're going to try and oxidize it, you won't get a color change. So what you add as your reagent is acidified K2Cr2O7. With the 1-ol, what happens is it goes from orange to green. Because when you're oxidizing something, you have to reduce something else, and it still applies here. You're oxidizing this into either an aldehyde or carboxylic acid. So this K2Cr2O7, mainly this is going to be reduced. And then here, for 2-methyl-butan-2-ol, no change. Now it says compounds A and B have this molecular formula that A has a singlet, a triplet, and a quartet in its H1 NMR spectrum, and B only has 2 singlets. Draw a structure for A and B. So we need to just list out the information first. So definitely know that we've got a C4H8BR2. Fine. Now, here it's told you it's a singlet, a triplet, and a quartet. There's another piece of information we can get out of here, is that there are 3 groups of peaks, so there's 3 hydrogen environments. Make sure you always write the number of environments down. That helps a lot. We need to divvy these up, basically, to figure out how we can get this to come out. So if it's a triplet, then that means the adjacent's got a CH2 next to it to this. If it's a singlet, the adjacent's got just no hydrogens on it. And then here, if it's a quartet, it means the adjacent's got a CH. So we need to figure out how we can divvy these up. So if I try and just say, well, if that's a singlet, that's a triplet, there's a quartet, this quartet might be from here. So I could do CH2 here, CH3 here, right? Now I'm left with a singlet. So this next carbon can't have a single hydrogen on it, right? So I'm going to put my BRs here and my BRs here. Then I compare with the rest. So I've only got 3 CHs here. Sorry, 3 Cs and however many Hs. 1, 2, 3, 4, 5. So I've got 3 Hs left. So I'm going to do CH3 and see if that works, right? If it adds up. So it says here we've got 3 environments. 1, 2, 3. There you go. This one would be a singlet because it's next to something with no hydrogens on it. This carbon has no hydrogens on it, right? This one would be a triplet because this one doesn't have any hydrogens, but over here we've got 3. Sorry, not a triplet. This would be a quartet, sorry. And this one would be a triplet because that has 2. So this is what A would be. Done. Now for B, it's told you that it only has 2 singlets, right? So that means you've got these hydrogen environments that are identical and they have the adjacent carbon has no hydrogens on it. And as well as that, there are just 2 environments. So I'm going to start with just working out. I'm going to start in the middle bit, right? So if I know there's no hydrogens on this carbon in the middle. So now I need to figure out ways of divvying up everything so that we have the BRs and whatever, but 2 different carbon environments to satisfy this. What I might do is if I were to put a BR and a BR here, right, then all I'm left with is however many C's are left there, right? So that would be what, like C, whatever, H something, right? But that wouldn't help, that wouldn't work, because the problem is that they would be identical, because if I were to do that, I would be left with what? So if it's C4HA, I'd have CH2, CH3, and then a CH3 here. Can you see how that's one environment, that's another, that's another? So we have 3 peaks. So I need to find out some way of making 2 of them identical. What I might try and do is I'll do CH3 here, CH3 here. Those are identical. I'm left with a BR. And what else am I left with? I'm left with a CH, what's that? 1, 2, 3, 4. So I'm going to have a CH2 left and a BR. If I do that, that's one environment. That's another environment. That's the same as that one. 2 singlets, 2 environments, done. So it's really important to narrow down what the environments are, because that's just something that people forget to just look at entirely for some reason. Every single proton or carbon-13 NMR spectrum, before I even look at the data sheet or anything like that, I always go look at the number of environments first, because then I know exactly how to structure what I'm doing. So compounds C and D both have this molecular formula, C6H3Br, which suspiciously looks like a substituted benzene. C has 2 peaks in its carbon-13 NMR spectrum, so it's got 2 carbon environments, whereas D has 4 carbon environments. So what this means is we've probably got a benzene here with 2 bromines substituted on in a way that there are 2 environments. So I'm going to try and make this as symmetrical as I can. So I'm going to put this here, here, and here. Because then this carbon and this carbon and this carbon are identical. That's one environment, but these are different. But they're all identical to each other, and these are different from the original BR, but identical. So that suits that one. Here, this one has 4 peaks, so I'm going to try and shift one of them across and see if that screws things up. So if I put a BR here, and like a BR here, and then like, I don't know, a BR here, so they're all next to each other. That's one environment, which is the same as this one, but then that one's different. So we've got 1 here, 2 here, 2 here, 3 here, 3 here, and 4. So then that's it, done. Compounds EF and G are isomers. Figure 1 shows the infrared spectra of these isomers, but not necessarily in the same order. So it says label each one with EFG in the box. So if we look at what E is, it's got a carboxylic acid group, and F has an ester. You should be able to immediately recognize that C110C is an ester, and here this is a ketone. So we need to figure out which ones fit in the bill for what. So immediately, one thing I can quite nicely take out is probably going to be the carboxylic acid one, because the other 2 don't really have that nice OH that the carboxylic acid would have. So if I go get the datasheet, one track. So rather than spending ages looking at each one of them being like, oh, this could be this could be that, blah, 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 I'm actively seeking out what I want. I know that this one's going to be easier to tell apart simply just because of that. So I'm going to go straight in for the kill and look for where the OH is in this one. Right? So if I'm looking for the carboxylic acid OH, I'm looking for a peak from 2,500 to 3,000. No. No. And would you look at that? 2,500 to 3,000. So that one's got to be E. So you kind of have to be tactical with your moves like that. You want to go in looking for what you want to get rid of rather than like go and actively work out each and every single one of them. Generally speak of these styles of questions. However, so for F and G, the differences here is I'm looking for a double bond O and a CO. And here it's got a double bond O and it's got an alcohol group. So an alcohol group's going to have a different range. So immediately I'm going to go in for the kill and look for the one with the OH, and that'll be the other one. So if I look here with OH alcohols, it's 3,250 to 3,550, which you can see is like what, like around here to there. So that's immediately that one. So that one's G. So then the other one's F. So you got to go and look in for what you're going to use as your differentiator. So again, the strat is I'm looking for carboxylic acid, then I'm looking for alcohol. The last one's the last one. No point going looking for each one of these, and because they're all there in every single one. And there's no point sitting there spending ages looking at every single one, being like, oh, there's this group, there's this one, there's this, blah, blah, blah. Go in and look for what you're going to use as your differentiator, being like, this is the one that I'm going to use to get rid of the others. So isomers X and Y have this formula. Give the IUPAC name for isomer X. So first of all, always work out the stem. So 1, 2, 3, 4, 5. It's pent. It's also cyclic, so we know it's going to be cyclo, right? And then we also see it's a ketone, so anone. I put a lot of space there. Whoops, it's cyclopentanone. There you go. Explain how and why isomers X and Y can be distinguished by comparing each of their boiling points, the carbon-30 spectra and infrared spectra. Use the tables A to C in your data booklet for your answer. So let's do it one by one first and start by the boiling points, right? So if we look at boiling points between the two of these, the fundamental difference here is that that's a double bond O, that's an OH. What do you spot? Oh, would you look at that? Hydrogen bond. Whereas that's just dipole-dipole, right? This alkene's not really going to do very much in terms of that. So then, here, number one is that Y has a higher boiling point because O bonded to H, hydrogen bonds, and they're stronger than what's in. You need to make comparative statements. It's stronger than X because it only has, X is only dipole-dipole interactions. Obviously, you write the whole thing. I'm just doing it for the sake of time because I'm lazy. And that means you're going to need more energy to overcome hydrogen bonds when boiling. There you go. You're not breaking covalent bonds because if you're breaking that, you're breaking this out into something separate. So do not say that. You are boiling. When you're boiling, you're breaking the bonds between things. So for example, Cl and Cl, right? Cl and Cl. If they got London forces between the two of them, you're breaking these forces, not the covalent bond. Otherwise, you'd have Cl and Cl, and that's wrong. Or with H2O, same thing. You're breaking the hydrogens between them because if you did that, you would just have H and O, and that's wrong. So you're not breaking covalent bonds. Please don't say that. So now it's carbon-13 NMR spectrum. Immediately, I'm going to go look at the environment. So we've got 1 here, 2 here, 2 here, 3 here, 3 here. Whereas 1 here, 2 here, 2 here, 3 here, 3 here. So unfortunately, both of them have 3 peaks. We should always say that in the carbon-13 spectra. So both have 3 environments. So they'd have 3 peaks. Then what you would do is you look at what X has. So X would have a peak here, right? Which is going to be, if I just look at the data sheet on my side, that's going to be, what, 20 to 50? And Y is going to have an OH here, which is going to be 50 to 90. Just rather than copy and pasting the whole thing, and you can just look at it your own time. So X has peaks at 20 to 50. Y has peaks at 50 to 90. We need to say Y because of the C double bond O and because of the CO here. There's no point saying there's peaks of 5 to 40 because that's in both of them. They want to know how you're differentiating them. Then the next one is to talk about IR spec, right? So if we look at IR spec, this is going to have a peak. If I still have no, I've cut it out. Well done-ish. If you look at the data sheet, this will have a peak at 1680 to 1750, whereas this peak will be at 3250 to 3550 as well. And it's also going to have the C double bond C, which means you're going to have a peak in the 1680 to 1620 to 1680. But as well as that, every single infrared spectra below that 1500 has like a very wiggly bit there. It's called the fingerprint region. Fingerprint region means if you have this molecule, if I have the same one, as long as it's pure, there's no impurities in it, we should give you the same fingerprint region no matter what, for every single given molecule. So you would say that, in that X would have a C double bond O peak at like the range 1680 to 1750, Cm minus 1. Y would have a peak at the OH, from 3250 to 3550. Wait, no, 3330, sorry. And then also C double bond C at 1620 to 1680. And then as well as that, they would have different fingerprint regions below below 1500 centimeters minus 1. Because, again, they're different molecules. Done. So paracetamol is a medicine commonly used to relieve mild pain. Traditionally, paracetamol has been made industrially in a 3-step synthesis using phenol. So we have phenol, and then for some reason there's an NO2 in it, and then there's an NH2, and then bang, this has happened. So immediately I can see that we're doing nitration of benzene, so that we're going to add this on somehow, right? But we got to swap off an H. So to me, that's electrophilic substitution immediately. From NO2 to NH2, we're adding H into it, so we're reducing it. And here as well, it even says that we've got NO2 and we've made an amine. Now, to me, I could see that this C double bond O has joined onto this amine group here. Now, I need to think, what can I react with an amine to stick a C double bond O on? I know that I will have added an acyl chloride. You should be able to immediately recognize what groups are in here and what's happened. Now, it says name the mechanism for step 1. This NO2 will have been added because you've reacted with H2SO4 to make this. It will have been stuck on here, but the problem is that the H would need to be booted off. When you're doing that, you're substituting, and the reason it's going for that benzene ring is because it wants electrons from that lovely, beautiful, delectable ring. So then it's electrophilic substitution. Now it says complete the equation for the reaction in step 2. Now, even if you forget, you can just compare side by side. We've got NO2 and H2. We're definitely going to be adding H2, right? Forget balancing. We can do that in a sec. We need to get rid of these O's somehow. They're not going to just be on their own, but we've added H as well. Most likely thing is you're going to make H2O, and then you can balance it like that. So we've got an H2 here, so that's 1, but then we have an H2O here as well. But we have 2 O's, 2 O's. So I can put a 2 H2O here. That's 2 of them plus 1 of them. It's 3 H2s like that. There you go. In theory, either ethanoyl chloride or ethanoic anhydride could be used in step 3. Complete the mechanism for the reaction of 4-aminophenol with ethanoyl chloride, and this RNH2 is used to represent the 4-aminophenol in this mechanism. So what's happening here is we're doing nucleophilic addition elimination. So we're adding something on and we're booting something off. So the first stage has already been given to you, where this lone pair of electrons, because it's a nucleophile, is adding on to this delta positive carbon, right? This carbon is like, I got too many bonds, bro. I got too many. I need to get rid of it because now it's got 1, 2, 3, 4, 5. So what it does is the only option it can do is boot off the electrons from this double bond to this oxygen. The issue, however, is now this oxygen has a lone pair and it's also negative. So we need to figure out a solution to that problem, right? So if I just draw the next arrows, so we have like more space, CH3, C. This is now a single bond here, O minus with the lone pair. I'm going to draw the here just for the sake of like simplicity, because it's always good to draw lone pairs. So it's easier to draw rather than this, right? And then as well as that, we've got a Cl here. Now we have this NH, R, well, R here and an H here. But the problem is now this has not got this lone pair anymore, and it's got too many bonds. So that's a plus, right? Now we're in a bit of a pickle, because this doesn't want to be an O minus with a lone pair of electrons. This carbon doesn't want too many bonds. So what's going to do is it's going to put these back into here like that. And as well as that, if you have a look in step 3, we have a double bond here, double bond O as well. So we need to get from this stage to back to double bond O. So you can do that as well, compare side by side. So the electrons must have gone back in here. Now this carbon's like, dang, I still do not like having 5 bonds. I need to boot something off. So rather than memorizing arrows, again, think about the logical steps. Here, this carbon has no Cl. So the Cl must have been booted off. So then if that Cl's been booted off, the electrons aren't going to go that way. This carbon would still have way too many electrons. It'd be negative. It's going to go from the bond to the Cl like this. Now, if we look down here, this NH3 with the NH2 with the R in is not happy. It's like I'm not chilling. And as well as that, if you have a look, it's only got one H here too as well. So what's happening here is that one of these H's has to be booted off to satisfy this. Now, we're not going to boot it off this way because then that'd make H minus and then that'd be N2 plus. The electrons from that H is going here. But this H has to be taken away by something else. In this equation, they've told you that we're reacting 4-aminophenol with 4-ethanol chloride. So what happens is another 4-aminophenol, because that's the only thing that's got an amino bit in it, like a nitrogen with a lone pair, right? Comes along and gives its electrons to that hydrogen like this. There you go. So then what you end up with is your final thing here, which is going to be CH3, C double bond O, NH, and then R, which is exactly this thing. In practice, ethanoic anhydride is used in the industrial synthesis versus ethanol chloride. Give one reason why. It is because it is dangerous to use. It like reacts way too violently. As well as that, you could say it's explosive, you could say it reacts violently, and you could say it forms a strong acid because it makes HCl, it's vulnerable to hydrolysis, all kinds of things, but it's just dangerous. So in step 3, other aromatic compounds are formed as well as paracetamol. Draw one of the structures. So if you look back here, what we've done is we've added an acyl chloride, remember? So an acyl chloride always has a C double bond O and a Cl, right? This is a phenol, which can also react with this as well. What happens is this OH, the H is gone, and what happens is this Cl is gone. So you end up making HCl, and this C bonds over like this. So what you end up getting is you get an H, C double bond O, like all the other stuff from this side. And then you've got an O, because the H is now gone, bonded to a C double bond O like this. And then the rest, which was whatever the bits and bobs were, which is that CH3 there. So what you've ended up making here is an ester link. Chemists have recently developed a 2-step process to produce paracetamol from phenol. In the first step, the phenol is oxidized to hydroquinone like this. In the second step, hydroquinone reacts with ammonium ethanoate to form paracetamol. Complete the equation for this second step. So if we have a look what's going on here, we have an OH and an OH, and for some reason this has now gone into this and some other stuff here. Right. Now, the question's told you it's reacting with ammonium ethanoate, right? So if we're drawing ammonium ethanoate, that's going to be NH4 plus, right? And then CH3COO minus, ammonium ethanoate. So this has reacted. What's happened is that this whole ethanoate bit stuck here with a bit of an H and an N here, right? So what we're left with is we're left with an O. We're left with an O, and this is NH4 plus. It's now gone down to NH. It's just one NH, right? So we've now got an H and a bunch of H's, right? And we've also taken an H off of here. So now we've got H2O probably is going to be what we've made. This has lost 3 and this has lost 1, so we've got 2 H2 on that side. There you go, done. So now it says calculate the mass in kilograms of hydroquinone needed to produce 250 grams of paracetamol. So just quickly scribble out what you're going to make. So hydroquinone, again, always just scribble out quick equations so you know the ratios is what I mean by that. So hydroquinone and something makes paracetamol. So hydroquinone, they're in a 1-to-1 ratio making paracetamol. write down what you know. So in paracetamol, we know we're going to make 250 kilograms, which is 250,000 grams. We know hydroquinone has an MR of 110. Now we can work out the MR of paracetamol, which is going to be, if we just add all of the atoms up in there, I'll just do it now. You end up getting 151, right? So we know they're in a 1-to-1 ratio. So in that case, the moles of the paracetamol is going to be, it's 250,000 divided by 151, which is 1655.6 moles. Therefore, they work in a 1-to-1 ratio, so you would need this many moles of that too. So the moles of the hydroquinone is also going to be 1.0 blah, 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 whatever, right? Therefore, the mass of the hydroquinone is going to be moles times the MR, which is going to be 110 times the 1.6 blah, 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 blah that we just worked out. If we do that, we get 182,119 grams, right? But they want it in kilograms, so you divide it by 1,000. But then we also want to follow the same number of significant figures in the question. So it's going to be this, basically kilograms, but we were just going to stick it to 182 like that. There you go. This question's about thin layer chromatography. A protein was hydrolyzed to form a mixture of amino acids. The spot of this mixture was added to a TLC plate, and the plate was placed vertically with a small volume of solvent 1. When solvent front was reached nearly to the top of the plate was removed and allowed to dry. The plate was then turned anti-clockwise through 90 degrees and placed vertically in a small volume of solvent 2. So they're doing 2 rounds of chromatography, thin layer on the same thing. When the solvent front reached nearly the top of the plate was then removed and allowed to dry, and here's the final thing. So what's happened is the original spot was here, it will have moved up this much, and then solvent 2 went this way, so it will have moved that way as well, right? So fine. It says suggest a suitable reagent for the hydrolysis of a protein. So when you're doing that, you're breaking the peptide bonds, which are amide links. So we're breaking CONH. What we're going to use is concentrated HCl, or a strong base, either's fine. There you go. So just how the positions of the amino acids were located, what you do is you add ninhydrin, which makes them go purple, or you could add UV light as well if you've got a plate that sort of glows when UV light's on it. It says deduce the minimum number of amino acids present in the original mixture. This is a mixture, remember, of different things which will separate out. So this separated out into these 3, but that doesn't mean they're amino acids because they further separated out. So remember, it separates and then goes this way. So if we look at this one, it's split into 3, which all then separated this way. So we've got 1 and 2 here. That came from this. So that they're 2 separate amino acids. We've got 1 here, we've got 2 here. This separated into 2 separate amino acids. We've got 3 and 4 here. And then this one also split into just 1, so that's 5. But then this one, remember, these didn't actually move upwards in the first solvents. They must not have been very soluble in the first one. So in that case, in the second one, they started to become solvent and move that way, which is where you get 6 and 7. So the answer is 7. It's devious, but you got to think about it step by step like that. There you go. Now it says, suggest why it was necessary to use 2 different solvents. Well, if you see here, these didn't move in the first one at all. So you could say that some amino acids, I'm writing that for short, you write the whole thing, did not separate in the first solution. There you go. A dicarboxylic acid has a relative molecular mass of 118 to the nearest whole number. Deduce the molecular formula of the acid. So I know it's going to have 2 lots of COOH in, right? Which means it's going to have 2 lots of that in. So if I do COOH, that's 12 plus 16 plus 16 plus 1, and it's got 2 lots of them, so I know it's got 90 already. So that means 118 minus 90 is whatever's left over. So 118 minus 90 gives you 28. So that 28 has probably got to be some amount of CH2s, right? Because each successive member in a homologous family or series of chemicals will subsequently go up by CH2. So that means how many CH2s can I fit in this? That's going to be 28 over 14, which is 2. So then the formula of this thing is going to be C2, 2 from the carboxylic acid plus another 2, so C4, sorry, H, and then 2 from here, and then 4 from here, so H6, and then O, well, there's 4 of them, so there you go, done. A student dissolved some of this dicarboxylic acid in water and made up the solution to this volumetric flask, and they titrated this, and then they got that, and then just calculate the mass in grams of dicarboxylic acid. You'd be surprised how many people jump into this without trying to do anything, and just be like, oh, I'm just going to mold this, I'm a genius. Like, don't, come on, step by step it. What they did is they got this dicarboxylic acid, I'm just going to write as this 2COOH because I'm lazy, and they put it in 250 centimeters cubed. Then what did they do? They took out 25 centimeters cubed of this dicarboxylic acid, and they added, what did they add? They got a 25 centimeter sample of this, and so they added NaOH, and they needed 21.60 volume, and that concentration is 0.109, right? And that's centimeters cubed. It says calculate the mass of the dicarboxylic acid that was used and give your answer to appropriate number of significant figures. You cannot do this without writing an equation, or at least knowing the proportion of things. So think about this. So we've got you don't have to write like a really perfectly balanced equation, just the basics. I'm going to be reacting a dicarboxylic acid plus NaOH. This is going to be 2 COHs reacting with one of these. So we're going to need 2 of those to react them fully. So it's a 1-to-2 ratio. So always do that. I can work out the moles of the NaOH needed to neutralize this much in 25 centimeters cubed, which is going to be its concentration times the volume. So it's going to be 21.6 over 1,000 times 0.109. If I do that, I end up getting 2.3544 times 10 to the minus 3 moles. Now I can see, because I wrote the equation down, because I'm not an absolute spoon, that there's 2 to 1 here. So that means the moles of the dicarboxylic acid in 25 centimeters cubed, which is why you should do this, is going to be a half of the answer. So if we do that, that means it's going to be 2.3544 times 10 to the minus 3 divided by 2, which is going to be 1.1772 times 10 to the minus 3. But the question is asking the mass in the original thing, which is here. So we need to times our answer by 10 to get the moles of the dicarboxylic acid, blah, 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 into 50 centimeters cubed, right? So that means the moles of this are going to be 1.1772 times 10 to the minus 2, right? Now, to find its mass equals moles times the MR, which is going to be this answer that we just worked out, the 1.1772 blah, 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 times to the minus 2, whatever, right? Times the MR, which is the same one here, which is going to be its MR of 118. And if we do that, we should get 1.389, but we want to keep the same number because of the question, so it's going to be 1.39. There you go. Compounds with the molecular formula C6H14O2 have a relative molecular mass of 180 to the nearest whole number, and this includes the dial below. Deduce the number of peaks in the H NMR spectrum of this. So then if we look here, there's 1 hydrogen environment, there's 2, these are different, there's 3. Here, that's another one, 4. Here, if we have a look, this carbon that it's stuck to is stuck to this, and this, right? This carbon's stuck to the same things. So that's actually the same as the previous one. This is going to be the same as this one, so there's 2. That's going to be the same as this one, so that's 1, sorry, and that's going to be the same one here as well, so that's 4. It's not just directly what's next to it, it's the entire position in the whole molecule that gives it its hydrogen environment. So that's what it is, because here it's symmetrical. There you go. So now it says, draw the structure of a different diol that has this formula, that has an HNMR spectrum of 2 singlet peaks. So if it's a singlet, remember that means the adjacent carbon has no hydrogens on it. So that means that all of these things that are picked up, the peaks that were picked up must be on carbons, which are next to carbons with nothing on it. So I'm going to draw what I know is in the middle, definitely. I know that they're going to have 2 carbons here with absolutely no hydrogens on them, right? And then I need to figure out ways of divvying up the rest of our hydrogens, and it's a diol, remember, to make sure we only get 2 peaks. So I know it's a diol, so immediately I'm going to have an OH and an OH here. What I'm left with is a bunch of, like, you know, whatever, C6, so we've used up 2 of them, so we've got C4, and we've got H, how many H's left is that? So 3, 6, 9, 12, we've got 12 H's left. I need to figure out how to divvy these all up so that they're all in exactly the same environment, because that's already 1 peak, that's the same, so that's going to give you the 1 peak, and they're going to be singlets, so I need to figure out how they do them, so I can put H3C, CH3, CH3, CH3. Those are all in the same hydrogen environment, so that means I'm going to get 1 peak for those. These are the same to each other, but different from these, so I get 2 peaks. They're all going to be singlets because these have no hydrogen atoms on them directly. There you go. So the dicarboxylic acid in 10.1 and the isomers in questions 10.3 and 10.4 all have a relative molecular mass of 118. State why the dicarboxylic acid can be distinguished between the 2 diols with high-resolution mass spectrometry with electrospray ionization. It's because when you're doing this, you can work out the precise relative molecular masses, which is to a lot more decimal places, which means have like blah, 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 0.0, like 0.0001 or something like that, right? And that can help you differentiate the 2 of them. Because obviously if we round them up, it's just going to look like a nice pretty 118. So what it means is we can work out the precise MR, and they are different. There you go. This question is about esters, including biodiesel. An ester is formed by the reaction of an acid anhydride with this alcohol. So complete the equation, including the structure of the ester, and give the IUPAC name as well. Every ester in the universe has C double bond OOC, right? Where this bit comes from the alcohol and this bit comes from the carboxylic acid. An acid anhydride is a derivative of a carboxylic acid. So this bit's going to give you the carboxylic acid part of the ester. So I know that we're going to have CH3, CH2, C double bond O, and then this alcohol bit sticks on here, that's gone. So in that case, sorry, no, this alcohol bit's stuck in here, sorry, and the O is gone over here. So then you end up getting CH2, CH3 like that. The other product, what we've got left is we have an H that needs to be used up, right? So what we end up with is we have CH3, CH2, C double bond O, H. So the ester that we end up making is 1, 2, 3, but that's the carboxylic acid derivative, so we know it's going to be propan no weight. And here, 1, 2, ethyl. So it's just ethyl propanoate. There you go. In a reaction to form biodiesel, 1 mole of vegetable oil reacts with an excess of methanol to form 2 moles of an ester with a molecular formula of this and 1 mole of an ester with a molecular formula of that. Draw the structure of the vegetable oil showing clearly the ester links. We should represent the hydrocarbon chains in the form CXHY, where X and Y are the actual numbers of these carbon and hydrogen atoms. So every single fat and oil will have a glycerol on it. So what that is this 1, 2, 3. It's going to have an H. It's going to have an H. It's going to have an H. It's going to have an H here and H here, right? And there's ester links between them. So there's going to be an O here, an O here, an O here. And then next is going to be a C double bond O, a C double bond O, and a C double bond O, because every ester link in the world looks like this. So if that's the case, then we have to just add the rest in. So they've told you that it's what? It's and 1 mole of an ester with this. You should draw the structure of vegetable oil. So this vegetable oil ends up giving you an ester with this and that. So that means that this vegetable oil should have however many left of each of these there is, really. So that means in this case, they're going to have, we've used up 2 carbons, 17, 17, 17, and there's going to be some amount of H's, right? So 17H. And in this case, there's 2 moles of this. So there's going to be 2 that make up, well, we've lost 2 already there. We've lost 1 here, and then we've lost some here. So however many hydrogens that leaves us with, because each time you make one, you're losing H2O as well, remember? So that means we're going to have 34 minus 2 H2Os, and then we're losing an extra 1, which means we're going to end up having, what, the H31, and then there's 2 extras here, but we're losing 3 of them, so H33. There you go. The compound C19H34O2 is the methyl ester of ZZ octadeca-912 dienoic acid. Parts of structure is shown below. Complete the skeletal formula to show the next pair of hydrocarbon chains. The parts of the hydrocarbon chain to the carbon number 14. In your answer, show the Z stereochemistry around the C11C bond. Fine. So we have a look. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. We've just got to join the next bits on, right? So it's the next part of the chain to the number 14. So I'm just going to add all of the ones up till then. So that's going to be what? So 9 here, 10, 11, and then 12, 13 to 14. So that's 1, 8, 9, 10, 11, 12, 13, 14. So that's our 14, right? Now, here, it is the methyl ester of octadeca-dienoic acid. So it's got 2 alkene bits in it, right? So if that's the case, we're going to have to add, and we also have to add our C-double-bond-Cs anyway, so there's already that in there. So this diene, so it's going to have 2 double bonds here, like this. Now, it's a Z, so it's going to be on the same side, so that's that, and then this is also going to be the same sides as well. So that's it, actually. There you go. Then it says, give an equation for the complete combustion of this. So we're going to do C, 19H34O2. We know we're going to add the O2. We're going to make CO2 and H2O. Start by putting what you know in first, then add the extras in. So we know that the C19, so we're going to make 19 of you. We know there's 34 H's, so we're going to end up with 17 H2Os, right? On this side, we're going to need how many oxygens? We're going to need 2 lots of 19 plus 17 oxygens, so we're going to need 55, right? We've only got 2 here, so we actually need 53, really. So that means we're going to have to add up 53. We're going to have to add 53 oxygens, which is 26 and a half. So you could do 53 over 2 there. Done. So combustion of biodiesel produces greenhouse gases such as carbon dioxide that cause global warming. Part of the IR spectrum for CO2 is shown. State how the IR spectrum is not what you might predict from the data table in A. So you would look at the data book. I've not copied it in A because it's just too much work, can't lie. But the data table says that it should be 1680 to 1750, but here that's not matching it, is it really? So you just say that, the peak here around 2300-ish, so the peak at 2300 does not match the 1680 to 1750 cm-1 in data booklet, because that's for C double bond O in like ketones, like aldehydes and stuff, like aldehydes and ketones and stuff. So then it says, explain how this causes global warming. So the idea is that they absorb infrared radiation, the bonds in them. So C double bond O absorbs it, right? And then IR, infrared radiation, is heat, right? Now what happens is normally here's the Earth, here's the sun over there. Heat gets here, and then it's normally reflected wherever, right? What's happening though is that these C double bond O's are absorbing that heat and actually holding it there, and not actually letting it just, reflect back from the surface of the Earth. And it's transferred to like other molecules, and what ends up happening is we retain the heat in this, and it warms the world like that. So in that case, that's what we're going to say, is that the C double bond O bond, the bond is what's absorbing the heat. It absorbs IR radiation. Therefore, IR radiation cannot be reflected by the Earth's surface and cannot escape. That's the bit you need to say. It's not the reflected bit. That still doesn't explain why. It cannot escape from the atmosphere. There you go. That's the latter part that's needed. You can't just say it isn't reflected, because that doesn't tell us why it's causing global warming. It's the bit that it can't get out. So figure 4 shows two complementary strands in a part of DNA. So what you need to do is you've got to look for where the DNA is unlike the nucleotide bases, because we're being asked to draw the hydrogen bonds, right? So phosphate, 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 sugar, sugar, nitrogenous base, nitrogenous base. So we need to draw the hydrogen bonds between them. You look at the data sheet and you can figure them out there as well. So here we've got there and there, right? So we've got a adenine and thymine base here, pair. And then here, there's going to be 1, 2, 3 like this. So we've got a cytosine and guanine here as well. There you go. Now it says draw a ring around each of the component parts that make up a cytosine nucleotide in the DNA shown. So you look at your data sheet and you have a look at where cytosine is. So if I look at cytosine in the data sheet, it's where basically it's this one here, right? So there's one part, that's the nitrogenous base, right? This is your sugar, right? And then here we've got our phosphate that's stuck to it like so, including the other one, sorry, there, whoops. So there you go, those are all three of them. Now it says state the meaning of the term complementary when it's referring to DNA strands. It means that you have hydrogen bonds between A to T and C to G. There you go. Now it says aqueous NABH4 reduces aldehydes but does not reduce alkenes. Show the first step of the reduction of the reaction between NABH4 and 2-methylbutanal. You should include curly arrows and explain why NABH4 reduces methyl-butanal but does not have any reaction with 2-methylbutanine. All right, let's go. So first of all, we draw our structure. So CH3, CH2, CH, CH3, and then C double bond O. So we need to figure out how this is actually happening. What happens is this O, it becomes a single bond and it breaks and then you end up with an OH. We're reducing it down into an alcohol, right? So then what's happening here is that something is causing this to cause this bond to break. It must be that this carbon has too many bonds, so it must have gotten a new bond from something. What happens with NABH4 is it actually provides H- of the lone pair of electrons. That's a nucleophile, so it goes here like this, and you've got this delta positive carbon, delta negative oxygen here. So when it does that, it donates its lone pair of electrons to this. You've now got a nucleophile coming on here, right? And it's been added on. So immediately, this is called nucleophilic addition. But the problem is this carbon's got 5 bonds. It's I need to boot something off. Won't boot you out, won't boot you off. And the way I like to think of it is the electrons are very close to this oxygen, right? This is like the final push, shoving it onto that oxygen like that. So then here, one of these bonds breaks like that. That's your first step. Then what you end up with is all the other bits and bobs where it's got like a C, O, like minus the lone pairs, but they only want the first step anyway, so it's fine. We need to figure out why, for some reason, it's going to go for the C double bond O, but not a C double bond C. The only difference between these is O versus C. So that means that this has to be electron deficient, and that's got to be all right with electrons, because that's the whole reason it's going there. It's a nucleophile. So that's what you'd say. H- is a nucleophile. The C in C double bond O is electron deficient, but in CC, it is electron rich. Therefore, the H- ion, it still doesn't explain why it's not going for that. It's actually because it is repelled by the C double bond C. There's so many electrons and so nicely, beautifully dense here. You know, it's not going to actually go for this, and instead attacks this instead. There you go, done. A student attempted to reduce a sample of 2-methylbutanal but added insufficient NABH4. The student confirmed that the reduction was incomplete using a chemical test. What could you do? So we have a carbonyl, right? And they're trying to reduce the carbonyl. So if they've got butanol and they're trying to reduce it, when you're reducing this, you're going down to COH, right? You're going back from this to this. So in order for this to be incomplete, what it means is that there's still some of this left. If that's the case, then you're going to have a positive test for a carbonyl. So your options are you can add Tollens reagent or Valings reagent, and it will show a positive test for these. So I'm just going to go ahead and say Tollens reagent. And what happens is you get a silver mirror. Reason being is because that's still being oxidized into a carboxylic acid and so forth. Whereas with this, it wouldn't actually do anything. It doesn't react with the OH, so there you go. Because if you'd fully reduced it, you'd have none of that left, so this wouldn't be positive. There you go. Thank you very much. I hope that helped. Please like, share, and subscribe. You know the drill.